Division, one of the four base operators, and perhaps the most complicated. It was likely the last operator you learned in grade school, and it makes sense. After all, the other operators are all relatively simple. Addition involves combining two groups, while subtraction is about removing a group from another. Multiplication is just repeated addition, or creating multiple groups of a specific size. However, division isn't just repeated subtraction, that's still a form of multiplication. Instead, division can be thought of as distributing elements into groups of the same size. However, the issue with division is that not all quantities can be divided into equal groups. This introduces the concept of the remainder. The remainder can be left as is, but it also can be further divided, leaving us with decimal values. And today I will focus on a specific set of numbers that leave an interesting pattern when you divide by them. Consider the number 7. An unpopular property of 7 is that it is the smallest long prime in base 10. But what does this mean? Perhaps the best way to show it would be visually. These are all the results of numbers 0 to 6 being divided by 7. If you look closely, you will notice some pattern. And this is what a long prime is. It is a number that has a maximal period decimal expansion of digits, which means that the sequence of numbers produced in division will be as long as possible, which is n-1. For the case of 7, it is 6 long. Another neat aspect of long primes is that all numbers who aren't multiples of them will be a part of the same sequence, like how 7 divided by anything leaves a similar cycle. In fact, knowing this, you can even impress your friends by asking them to give you any integer between, say, 1 to 100. And for example, they could pick 72. And all you have to do is find the quotient and the remainder of 72. Here, the quotient is 10 and the remainder is 2. Then, you can exploit the fact that all division by 7 will leave the same decimal pattern, apart from when the remainder is 0, which isn't the case here. The only thing left now is to think about what point the sequence begins for our remainder. Different remainders will start at different points of the repeating sequence because they obviously can't be the exact same value. But luckily, finding which number a remainder begins with is easy and logical. The bigger the remainder, the bigger the starting point, as shown here. So in this case, we have a remainder of 2, which is associated with 2, therefore it begins at 2. And then we can continue our sequence. 2, 8, 5, 7. If you want to make it harder for them to figure it out, don't go past the 6th decimal. Otherwise, if you just start saying 285714, 285714, 285714, they might pick up on what's going on. But why is this happening? There's actually a pretty simple way to demonstrate this, and it involves long division. If you want to figure it out yourself, feel free to pause the video and give it a try. In this animation, we are dividing 10 by 7 using long division. For those unfamiliar with long division, the way it works is instead of dividing directly both numbers, we look at how many times 7 can fit in 10. In this case, 7 can only fit once in 10, and we write that 1 on the right. Then we remove that 7 from 10, leaving us with 3 as a remainder. Now, we can't find how many times 7 can fit in 3, but that's fine because we can multiply 3 by 10 and find how many times 7 can fit in that one. Of course, since we multiplied by 10, the value will be 10 times bigger than it should be. So to compensate, we'll write the answer in the 10th place, where it is 10 times less valuable. Then we continue doing this process. 7 fits 4 times in 30, so we can remove 28 and write 4 on the right side, and 2 on the left. Now again, we multiply by 10, giving us 20. Now you'll find that if we keep doing this, we end up reaching 10 again, which is right where we started. Because of this, the decimal values will repeat forever, because they will never reach a remainder of 0. This isn't that special. If we divide 10 by 3, we get this instantly. Yet what's special about 7 here is that before we arrived back at our starting point, we went through every single remainder that 7 can have, apart from 0. Hence, it doesn't matter what integer you divide 7 by, the remainders will lead to every other remainder, except 0. They are all in the same kind of loop. There is a neat way to represent this, and it is with the remainder cycle representation that I have thought of. In here, we have a cycle that shows where every remainder will lead to. Notice how the remainders of 7 all exist on the same cycle, except for 0. Now unfortunately, 0 cannot be included in the bigger cycle because 0 will always lead to itself. 0 divided by anything will always equal 0. Hence, we can't have a cycle of every remainder, yet we can have a cycle of every remainder excluding 0, which is what a long prime has. We can also notice other patterns in this form of representation. If a remainder will eventually lead back to itself, it will represent an infinitely repeating pattern in the decimal values. The size of that loop determines how long each sequence will be. For the case of 7, it is 6 long. For the case of 3, it is 1 long. If, however, a remainder points back to 0, then the amount of steps required to reach 0 is how many decimal places there will be. For the case of 1 divided by 8, there are 3 steps required to reach 0. Hence, we have 3 decimal places. However, if we were to look at 2 divided by 8, we'd notice only 2 steps are required, which is why there are only 2 decimal places after the point. One other neat thing to watch out for is how 1 divided by 8 ends in the same way that 2 divided by 8 ends, with 2 and 5, because 1 leads to 2, and once it has led to it, it will follow the same pattern. Alright, so we know what a long prime is and why it happens, but how can we find them? One way to do so would be to exploit a tightly related concept in math, primitive roots. Now, in what way are primitive roots related to long primes? Well, for reasons I'll explain later, if a number b is the primitive root of n, then n is a long prime in base b. That's neat, but still, what are primitive roots? The definition of a primitive root is that a number b is a primitive root modulo n if every number a coprime to n is congruent to a power of b modulo n. Now that's a lot of words, but what do they mean? First, let's talk about modulo. In here, modulo is referring to the function mod. Mod is a pretty simple function. It is all about getting the remainder. For example, 10 mod 7 just means what is the remainder of 10 divided by 7? The answer is 3. Different numbers can have similar answers with the mod function. For example, what will be the remainder of 17 divided by 7? Again, the answer is 3. We can say that 10 and 17 are congruent in modulo 7 because they give the same answer. Now, back to the definition. All we're saying is that if we were to raise b to the power of any integer, we must be able to get all coprimes of n. Coprimes are just numbers who share no factors. For example, 4 and 9. Perhaps a good way to show it would be with a demonstration. In here, we are testing to see whether 10 is the primitive root modulo 7 or not. In order to do so, we must go through all powers of 10 and find their values modulo 7. Now, we are looking to see whether every coprime of 7 below 7 can be found using this way. Two numbers are coprime if they share no factors, and since 7 is a prime number that shares no factors with any other number, this just means that we are looking for whether all numbers from 1 to 6 are present. In this case, they are. So 10 is a primitive root modulo 7, which makes sense because 7 is a long prime in base 10. But why does a seemingly random test determine whether or not a number is long prime? Well, essentially, what we are doing here is we are multiplying by 10 on every step and finding the new remainder of 7. Another way to see it is that we are moving the decimal point 1 to the left, which allows us to cycle through the decimal values. At first, 10 divided by 7 is only 1.42857, yet if we multiply by 10, we get 14.2857. The decimal value has changed and has moved 1 to the left, and if the decimal value has changed, then the remainder has necessarily also changed. You can't have two different values for the same fraction. Therefore, we are able to cycle to the next remainder just by multiplying by 10 and putting it on modulo 7. In other words, this test is simply cycling through all remainders and testing to see if there is a remainder cycle that has every remainder above 0. We can clearly see that when we look at examples such as 7 and 8's remainder cycle, the primitive root test gets remainders that follow through the same path as depicted on the remainder cycles. In here, 8 has failed because there is no path that leads to every remainder. So when we conduct the test, there is just no way to go from a remainder of 2 to a remainder of 5, for example. You might have noticed throughout my explanations that I have used 10 in the primitive root test and that I have mentioned base 10 a lot. The reason for this is because bases actually have an influence on whether a number is long prime or not. But what even are bases? Consider the digit 1. In this case, how much is 1 worth? Well, just 1 obviously. But what if I were to add 4 next to the 1? Did I just add a 4 to the 1? Is 1 4 equal to just 5? No, that doesn't seem right. Everyone knows that 1 4 is equal to 14, a bigger number than 5, and that in this case, the digit 1 is equal to 10. So we're doing 10 plus 4, which is 14. Well, actually, that doesn't have to be the case. Roman numbers don't function like this. Instead, adding another digit is just adding another number. So why do we suddenly have our digits getting bigger just because there's more numbers to the right? That's because we are all using the base 10 counting system. In order for us to be able to write bigger numbers in a more compact manner, we attribute different values depending on the position of every digit. For the case of 14, the 1 is in the tens, so we multiply it by 10 before adding it to the total. But 10 isn't some universal number. There is nothing special about 10. We probably just chose it because we just so happen to have 10 fingers. And in reality, we can substitute 10 with any other integer. That's what other bases are. Although if we were to change the base, we'd have to change the way we write a number. For example, in base 2, otherwise known as binary, this is how 14 is represented. If you were to do the math, you'd find that it adds up to 14. You might also notice how we only use 1s and 0s to represent 14. That is because in base 2, those are our only available digits. For the same reason that in base 10, we only have up to 9, because we count up to 9 and after that we go up a position. 10 is just 1 and 0, it isn't a character of its own. In base 2, we count up to 1 before going up a position. If we used a higher base than 10, then we would need more digits. In base 16, for example, letters are used for numbers higher than 9. All this to say is that changing a base can drastically change the way a number is represented. And this isn't exclusive to integers. Decimal values are affected too. If we divide 1 by 3 in base 10, we get 0.3 repeating. Yet divide by 3 in base 9 and you get 0.3. Suddenly, 1 divided by 3 is no longer a repeating decimal, it's just 0.3. This is where we come back to long primes. In fact, while 7 is a long prime in base 10, it isn't necessarily long prime in other bases. This raises the question, are there other numbers that can be long prime but just aren't in base 10? This is a script in Python that essentially just runs the primitive root test on a bunch of numbers in whatever base we want. Here is the list of long primes that is found for base 10. As a side note, 2 is being falsely identified as a long prime because the code is only looking for repeating remainders, it only checks for one remainder of 2. In other words, the lack of remainders of 2 means that the definition of a long prime doesn't make much sense in the case of 2, and so we consider 2 to not be a long prime. So let's change up the code to exclude 2. Now, let's instead change up the script by testing whether a number can be a long prime in another base by testing it in all other bases up until 100 and including it in our list if it qualifies in just one. Seem familiar? That is because these numbers are all the prime numbers above 2 and below 100, and the long primes keep going. The script just stopped at 100 for practical purposes, although the script never was asked to only test prime numbers. It tested every number to 100, yet only prime numbers qualified. Essentially, this script is hinting at the fact that non-prime numbers can't be long primes no matter the base, which doesn't seem that surprising because they're called long primes. But still, just because they're called long primes is not really a proof of why this is happening. Well, as it turns out, yes, the fact that only prime numbers show up is not a coincidence. When we claim that a number is long prime, we are saying that if we are to divide by them, they will leave a repeating sequence that is n minus 1 long, which is equivalent to how much remainders they can have excluding 0, because 0 will always point back to itself. We're also claiming that if we were to divide any integer by our number, they will be a part of the same n minus 1 cycle, just like how any integer divided by 7 puts us at the same 142857 repeating cycle. Yeah, what would happen if we tried the same on a composite number like 21? If we were to divide 1 by 21, we get a repeating cycle that is 6 long, which already shows that it isn't a long prime in base 10. Although, that doesn't prove anything. There are many prime numbers who aren't long prime in base 10, so what of it? Well, the exception here is that I'm not claiming that 21 isn't a long prime in base 10. I'm claiming that 21 is never a long prime in any base because it isn't a prime number. But why? Well, look at what happens when we divide 3 by 21. That's strange. This repeating sequence is the same that we get with 7. Well, the reality is that 3 divided by 21 can be simplified to 1 divided by 7, no matter the base. And as a result, the maximum length of 3 divided by 21's repeating sequence is that of 1 divided by 7. Yet the longest sequence a number can have is n minus 1, since it is related to how many remainders they can have excluding 0. And for 7, it is 7 minus 1, or 6. Yet, for 21 to be long prime, we need a sequence of 21 minus 1 long, or 20. 3 divided by 21 will never be able to be that long. Therefore, 21 can never be a long prime. And this isn't exclusive to 21. All composites are subject to this, since composite numbers have factors, and when their factors are divided by them, the fraction can be simplified no matter how big they are, no matter how small the factors. The reality is, as soon as you can simplify the fraction, you can't have a long prime. Take a look at 194. 194 is just 97 times 2. 97 is a long prime in base 10, so it will leave us with a repeating sequence of 96 long. And since 194 is just 97 times 2, 2 divided by 194 is just 1 divided by 97, which equals this monstrosity. The pattern is long, no doubt. Yet just because it looks long doesn't mean it counts. 194 requires a pattern of 193 long to qualify. Yet because of the fact that this is dividable by 2, the best it can have is a pattern of 96 long. 194 can never be a long prime, and neither can any composites. Alright, so we know that only prime numbers can be long prime, like the name implies, but again, they don't seem to always be long prime in every base. Take a look at the number 5. When we divide 1 by 5, we get 0.2, which is quite the short pattern. 5 is not a long prime in base 10, yet that doesn't mean it is never a long prime. To find the bases that 5 can qualify in, we can run this code, which goes through all bases from 0 to 25 and checks for matches. Running this code, we get this list of bases where 5 acts as a long prime. Now, if you were to take a closer look at the bases, you might notice something interesting. In this set of numbers, there are two patterns. One starts at 2 and goes up by 5 every time, and the other does the same, yet starts at 3. For example, 2, 7, 12, 17, 22, or 3, 8, 13, 18, 23. In fact, if we were to keep testing, this pattern doesn't stop, and thus it seems like the bases that 5 will be long prime in are 2 plus 5n and 3 plus 5n, where n is any natural number. And this isn't unique to 5. Here are the bases that other prime numbers are long prime in. They all seem to have a predictable pattern. It seems like if a prime number is long prime in a base, then if we were to add that prime number to the base, it will still be a long prime. But why is that the case? Well, firstly, let's take a look at what happens when we conduct the primitive root test on the number 7 in the bases 3 and 10. Now we know that with 10, the test should work because 7 is the long prime in base 10. But we're also affirming that since 3 is just 10 minus 7 and that 10 works, then 3 should work too. But does that hold true in the test? Let's find out. As you can see, it does hold true. 3 is giving us all the remainders of 7 apart from 0 in the primitive root test. But that's not all. If we were to look at the two tests side by side, we can see that they give us the same remainders for every iteration. 3, 2, 6, 4, 5, 1. And that right there is our answer. They will both work because they both have the same results in the primitive root test. But that's just one example. how about we instead prove it with algebra? We are claiming here that b to the power of any integer, y modulus p, will be the same as b plus p to the power of y modulus p. Essentially, if this is true, then we'll always get the same results in a primitive root test if the first base and the second base are p apart. So let's test it. Let's start with the first degree, with y equals 1. This is the easiest one to prove. We're just saying that b divided by p and b plus p divided by p should give us the same remainder. And that is true, because adding another p to b will not change the remainders. It will just form one more group. It's like adding 7 people to a group of 3 to help them form groups of 7. It wouldn't help. The 7 new members can just form a group within themselves and the 3 will remain as remainders. Alright, but what about the second degree with y equals 2? Well, let's take a look at the numeral example of this. We can expand 3 plus 7 squared into 3 plus 7 times 3 plus 7. Then we can distribute the 3 plus 7 into both 3 and 7, giving us 3 times 3 plus 7 plus 7 times 3 plus 7. Now again, on the right, we are adding 7 times 3 plus 7, and then asking for the remainder when we divide into groups of 7. If you had a classroom with however many people, and you had to group in groups of 7, then the remainder wouldn't change no matter how many other groups of 7 were added into the classroom. So 7 times 3 plus 7 is just a bunch of groups of 7 being added, and so they will not impact our remainder in modulo 7. And so they're basically just congruent to 0 in modulo 7 and can be thought of as addition by 0, and thus they can be removed. We are left with 3 times 3 plus 7, which when distributed gives us 3 times 3 plus 7 times 3. We can again discard the multiple of 7 for the same reasons as before, leaving us with 3 times 3, which is the same as 3 squared. Hence, both sides are now equal. And if we were to look at the cubic example, where y equals 3, we can again keep discarding multiple of 7 until all we're left with is 3 cubed. This goes on for any power, and thus as long as both bases are separated with some multiple of p in modulo p, the primitive root test will always give us the same results because of the way we can discard multiples of p in modulo p, which is why we get such predictable patterns for where a prime number will be long prime in. So we know that prime numbers have a predictable pattern for which base they will be long prime in, but is there such a case for bases? Well, let's try to find one. In this code, we can see all the long primes of base 10 until 100. Again, we can notice how all these numbers are prime, yet there is not every prime number in here. Looking closely, a pattern isn't easy to be found. Perhaps we lack the data. How about switching to another base? Let's try to look at the long primes of base 2. Will they be any more helpful? Not easy. How about base 3? Still, nothing really remarkable to be noted. Let's continue though. How about base 4? Alright, it seems like base 4 has no long primes until 100. That's strange. Other bases had plenty of long primes. Why does 4 specifically have nothing? Well, luckily for 4, it isn't alone in this. Here are all the long primes in base 9, or in base 16, or in base 25. They're all empty. Base 4, 9, 16, 25, none of these bases have long primes, while every base around them seems to have some. Why them specifically? Well, the truth is, they all share one common characteristic. Can you find it? They are all squared numbers, and of course, they're not the only bases that have no long primes. If we were to continue, we'd find that none of the squared numbers have long primes. But why? The reasoning goes a bit like this. Squared number bases can't have long primes because squared numbers can't be primitive roots of any number, which implies that squared number bases can't have a long prime. But again, why is that the case? Looking up for proof online for why squared numbers can't be primitive roots, I didn't really get any clear answer, only finding this proof on Math Stack Exchange. And if you see this and have no idea what it is saying, then luckily for you, I have no idea either. So the internet wasn't able to satisfy my thirst for understanding this seemingly out of nowhere claim. So instead, I made my own demonstration, and I believe that while it might not be as elegant as whatever this might be, it is a lot simpler to understand and a lot more intuitive. Let's come back to our primitive root test and consider two different bases, b and b squared. I will explain more on the numeral side, but there is also the algebraic version of the demonstration on the left. So in here, we have 10 and 10 squared, which is 100, and we are testing for whether the number 7 is the long prime in these bases. Going through our primitive root test, we can see that 10 qualifies, but 100 doesn't. Instead, 100 seems to go through the same remainders twice. But that's not all. If you were to look closely on the values that 100 is giving off, you might notice something interesting. 2, 4, 1. It seems like both base 10 and 100 seem to have a kind of connection in both tests. And this makes sense, because they are very connected. So connected that we are literally testing the same numbers. In fact, putting 100 to the power of anything is the same as putting 10 to the power of anything times 2, because of the power rule displayed on the left. Since 100 is like multiplying 10 twice, then if we were to multiply by 100 3 times, it's like if we multiplied by 10 twice 3 times, which is just multiplying by 10 6 times. So when we conduct the primitive root test and raise 100 to these powers, it is like if we are conducting the same test on 10, but instead raising it to the power of even numbers, such as 2, 4, 6, 8, and so on. Unfortunately, this is what is causing our issues. Like we mentioned before, the primitive root test involves going through the remainder cycle. If we do so for 7 in base 10, this is what we get for our first 6 elements. There is no repetition because there are 6 remainders to go through. Yet, what if we were to continue? Well, the cycle of 7 has only 6 remainders, so if we check the 7th, we will loop back. So by going above n-1, we are risking repetition, because no matter the number, the remainder cycle can't be longer than n-1, so we will have to revisit our remainder at some point. Yet, on the right, for 100, since it is the same as using 10 but multiplying to the power of 2, we are going over n-1. In this example, we are going all the way to 12, which puts us at risk of repetition no matter the number. In this case, we do repeat, since 7th remainder cycle repeats every 6 elements, and so 10 to the power of 2 and 10 to the power of 8 give us the same remainder, and thus because of this, 100 fails the primitive root test for 7. But this just might be the case for 10 and 100. Maybe this doesn't happen to all square numbers, or does it? Let's consider the case of the prime number 5 and two bases, b and b squared. Let's consider that in base b, p is a long prime, and so the cycle length of the remainders will be 5 minus 1, which is 4. Let's represent the remainders with different colors. Then let's write below at what power of b to modulo 5 gives us these remainders. Let's also include the b squared values below. Finally, let's draw two circles. The white circle represents the remainders we will get when we conduct our primitive root test with the base b, and the gray circle represents the remainders we will get when we conduct our primitive root test with the base b squared. When we look at what happens with the white circle, we can see that there are no repetitions, because the white circle needs to visit only 5 minus 1 squares, and jumps only by 1 every time, and so it doesn't reach the next cycle before it is done. But now, we need to do the same test with the gray circle, which will instead jump by 2 every time, because it is b squared, but still needs to visit 4 squares. So again, since we're jumping by 2 instead, we will reach the next cycle and we are at risk of repetition. And indeed, we can see that once it goes through to the next cycle, the gray circle jumps again to the same blue and red squares. And that is not a coincidence. If you try that with any prime number, the same thing will happen every time. The reason for this is because all prime numbers are odd, except for 2. But 2 never qualifies anyway. Yet we need a cycle of p minus 1 for this to work. If you're wondering why we need the cycle to be of length p minus 1, well, if our cycle was shorter, then we wouldn't even have enough remainders in the first place, and the square number base would have been screwed from the start. Imagine being asked to pick from a bag full of red cubes. Is it possible for you to be able to pull out any green cube? The answer is no, and no matter what you try, whatever strategy you attempt, you will never pull out a green cube. Alright, but still, why does the cycle length of p minus 1 screw square numbers over? Well, because all prime numbers apart from 2 are odd, then removing 1 from them will always give us an even number. So no matter the prime number, if it is a long prime, the cycle length will be even. Yet at a squared number, the gray circle has to make jumps of 2 rather than 1. When we add an even number to another even number, we will get an even number. When we make jumps of 2 from an even number, we will go through every even number. If I start at 2 and keep adding 2, I won't magically skip over 4 or 6. It just isn't possible. Yet we're saying that the cycle length of a long prime is always even. So by constantly adding 2, we can't skip over the cycle length. So instead, we will arrive right on it every time. And that's our problem. We're unable to skip over the cycle and access the other remainders. In this case, we repeat the same remainders at 2 and 6. We also repeat at 4 and 8. To not have repeated will require us to somehow reach 5 and 7. Yet those are odd numbers, and we are only adding 2 to even numbers. It is thus impossible for a squared number base to have a long prime if the number is long prime in the squared number base, like 110. But just like we said before, a number p can only be long prime in a squared base if it is long prime in the squared root of that squared base. Yet at the same time, we just claimed that a number p cannot be long prime in a squared base if it is long prime in the squared root of that squared base. Essentially, the only case where it could have been possible isn't possible. Hence, it is literally impossible. Alright, but what about cubic numbers? This Python script will tell us all numbers that are long prime in base 8, which is a cubic number. And as you can see, there actually are long primes in a cubic number base. But why don't cubic numbers suffer through the same issues as squared numbers? Well, as it turns out, they slightly do, although not as drastically. Take a look at the long primes in base 8. Can you spot what they all share, apart from being prime, of course? Need a hint? Here is every one of these numbers minus 1. If you know your divisibility rules, you know that to determine if a number is divisible by 3 or not, you can add every digit of that number and determine whether that number is divisible by 3. And is that the case for any of these numbers? No. For all long primes in base 8, if we remove 1, the result is not divisible by 3. But why does that matter? Because remember, the cycle length of long primes are p minus 1, and thus their cycle length is not a number divisible by 3. And that's why it's possible for cubic numbers to have long primes, because there are long primes with cycles that aren't divisible by 3. And that's important because the base is a cubic number and can be thought of as making jumps of 3, for the same reason squared numbers can be thought of as making jumps of 2. So now it is actually possible to skip over the same remainders when going to the next cycle, because the cycle length in their case can't be divided evenly by 3. And like with squared numbers, where every long prime cycle is even. Now finally, what about quartic numbers or higher degrees? Well, for the same reason as cubic numbers, there are no issues for higher degrees, except for degrees that can be expressed as square numbers, such as 2, 4, 8, 16, 32, and so on, because those numbers can still be thought of as squared. 3 to the 4th power can be thought of as 3 squared times 3 squared, which is 9 squared, and thus 3 to the 4th power is also a squared number and can't qualify. The same logic applies to 7 to the 8th power and so on. But hold on, let's step back a bit and combine two of our discoveries to make one final cool realization. Like we mentioned before, if a prime number is long prime in some base, b, then it will also be long prime in any base that we obtain as long as we keep adding or removing p. For example, 7 is long prime in base 3, therefore it is also long prime in base 10, 17, 24, and so on. Yet if 7 is long prime in all these bases, then these bases all can have long primes. But wait, didn't we also say that no squared number base can have a long prime? Wouldn't that mean that starting at 3, if we keep adding 7 on and on, we'll never get a squared number? Well, yeah, basically. We would actually never get a squared number, no matter how much we keep trying. Somehow, both infinite lists will never intersect. But that's not all. Every prime number is long prime in an infinite list of bases with predictable pattern, and with the same logic, none of them intersect with squared numbers. Let's consider 5 for example. 5 is long prime in base 2 and 3, yet also 7 and 8. And because the base we're using, base 10, is divisible by 5, if we keep adding 5, we'll get back the same unit digit, 2, 3, 7, 8. So this is implying that there are no squared numbers that end in 2, 3, 7, 8. And as it turns out, that is the case. Squared numbers might be infinite, but they sure do have a lot of restrictions. 5 is the one who gives us the most interesting pattern because we're using base 10, which is divisible by 5. So restrictions with adding by 5 are also easily predictable, such as numbers ending here with 2, 3, 7, 8. But we don't have to stick to base 10. We can use other bases to make interesting discoveries. Take the example of the prime number 3. 3 is long prime in base 2, and because of that, it is also long prime in 5, 8, 18, 14, and so on. If we were to represent these numbers in base 3, they would all look like this. You can notice how all these numbers end in 2, which means that no squared number can end in 2 in base 3, which is the case. Perhaps a more interesting way to phrase it would be to mention divisibility by 3. If we were to add 1 to all these numbers, they would all become divisible by 3, which means that if we were to add 1 to any of the squared numbers, none of them will be divisible by 3. 3 and 5 aren't the only numbers that we can do this to. With this list, we can make up as many rules as we'd like. For example, if you were to add 2 or 4 to any squared number, you'd find that none of them would be divisible by 7. If you were to add 3, 4, 6, or 9 to any squared number, then again, none of them would be divisible by 11. And you can keep doing this. And somehow, despite our never-ending list of restrictions, the squared numbers, which is also an infinite set of numbers, never intersect and never break any of our claims. And that's the reason I like math so much. Math can be so counterintuitive, it can be so random at times. We started off with a simple observation of repeating sequences of numbers, then we realized for some reason only prime numbers could qualify. Two completely different concepts were interlinked in this situation. But again, that wasn't enough. There was a lot more to discover. When we tried to see which bases prime numbers qualified in, we noticed a predictable pattern that was related to modular arithmetic. Again, bringing new concepts just to understand our initial observation. Lastly, when we tested the reverse, we noticed that most bases had long primes, except a specific few, the squared numbers, which in my opinion is the most out-of-nowhere realization that we made today. The explanation for the two other concepts were a lot simpler than that of the squared numbers, because these ones had a deeper connection. They somehow were caused by odd numbers being incapable of remaining odd if we were to remove one from them, thus always becoming even and divisible by 2. And all of this also led to our final realization that no squared number ends in 2, 3, 7, 8, or that no squared number plus 1 is divisible by 3. Somehow, having just started from repeating sequences, we arrived at a claim that is so far away from our initial point. Isn't that neat? We essentially went on a math journey. The numbers just spoke to us and guided us, and it was up to us to carve the way. I find this kind of math most fun when it is explored individually, rather than using a textbook or watching a video. This video has been essentially a showcase of my own exploration. In fact, I didn't know what to call long primes even as I started writing this video. I had actually thought of calling them the double chain numbers because they only had 2 remainder cycles, and to my disappointment, they had a much more boring name, long primes, or full repton primes, whatever that means. It was only after googling tricks to divide by 7 that I finally found mention of these kind of numbers online. But guess what the people talking about those numbers focused on most? The cyclic numbers, which are the numbers produced by long primes. They all have their own neat patterns, and if you're curious, Numberphile has a great video talking about them. I'll leave a link down below for those interested. But the cyclic numbers were also never mentioned throughout this video, because I wasn't as interested in their patterns as I was interested in long primes in different bases. So this video was guided by my own curiosity, and the discoveries were personalized to my liking. And that's exactly what I mean. Only you can satisfy your personal curiosity. Thank you for watching.